The next type of kernel services is the time management. The timer tick interrupt is handled by the timer interrupt handler. So, all of you know there will be an interrupt handler to handle the timing, to make use of the clocks. So we make use of the same interrupt handlers. Now, the timer tick interrupt can be utilized for implementing the following actions. So, for what purpose we are using? We, we are using it to save the current context in the currently executing task and increment the system timer time register by 1. So it has to increment the timing by 1, generate timing error and reset the system time register if the timer tick count is greater than the maximum range available. So for example, per day 24 hours, after that it has to come back to 0. So if it is greater, it has to reset. Now update the timers implemented in kernel. So increment or decrement the timer registers for each timer. That is depending on the count direction setting for each register. So the embedded application also may work on timings. So in that case, if at all there are any issues, then we may have to increment or decrement. So in case of incrementing register, we'll be making setting equals count up. So the count gets incremented. Otherwise, in case of decrement register, the setting we will be going for count down. Now activate the periodic tasks which are in the idle state. So we have to activate the many tasks which has to be periodically executed. So which are idle. So those tasks has to be activated. That is done by this timer. Invoke the scheduler and schedule the task again based on the scheduling algorithm. Invoke the scheduler. So wherever the scheduler is there, it has to be invoked based on the scheduling algorithm. Delete all the terminated tasks and their associated data structures. We know that for every task there will be TCBs. So once it is deleted, its data structure also should be deleted. Load the context for the first task in the ready queue. Due to the rescheduling, the ready task might be changed to a new one. So whenever there will be a rescheduling, then that particular task should be changed to a newer one, which has to be preempted by the timer interrupt. So it waits. So it waits for a specific duration of time. Still, if that particular task or process is there in the ready queue, it has to be removed and a new task should be put. That has to be monitored by the timer. Now, let's go to the next type. So here we are going to deal with hard real-time and soft real-time system. As usual, a real-time operating system which strictly adheres to the timing constraints for a task means timing is very crucial. So that type of applications, we call it as hard real-time system. A hard real-time system must meet the deadlines for a task without any slippage. You cannot bear the delay. Missing any deadline may produce catastrophic results. It may lead to a disaster, including permanent data loss and irrecoverable damages to the system. We may not recover that particular data anymore. So we should work carefully with hard real-time systems. Something like this, it works on the principles like a late answer is a wrong answer only. Though it is correct, because it is late, it is considered as wrong answer. It's kind of a principle. So the best examples are airbag control systems, anti-lock brake systems of vehicles. So in the automobiles, we make use of this airbag control systems and anti-lock brake systems. Those are the typical examples of hard real-time systems. Now, as a rule of thumb, hard real-time systems does not implement virtual memory model. So it cannot go for virtual memory model because in case of virtual memory model, there will be swapping that creates delay. So that is the reason they don't go for virtual memory model. Henceforth, this eliminates the delay in swapping out the task between the primary memory and the virtual memory. So because of this, there will be no delays. The presence of human in the loop for task introduces unexpected delays in the task execution. So this kind of system, if we try to involve humans there, it may lead to additional delays. So most of the hard real-time systems are automatic. Completely, it is automatic, and it will not involve human in the loop. There will be human. There will not be any humans in this particular type of systems. So it has to be dealt carefully. So now coming to the soft real-time systems. So in case of soft real-time systems, it doesn't guarantee meeting deadlines. So even if there is a delay, it is fine. But it offers a best effort to meet the deadlines. Though it cannot achieve anything at a specified time, it may achieve little later. So missing deadlines for tasks are acceptable. In this kind of system, it may be acceptable. If the frequency of deadline is missing within the compliance limit of the quality, if the delay is not too much, then definitely it is acceptable. A soft real-time system emphasizes on the principle of a late answer is an acceptable answer, but it could have done bit faster. Means it's a late answer, but still it is acceptable. Uh, but it would have been done faster. Means we can still forgive it. Now, the soft real-time system must often have a human beings in the loop. In this soft real-time system, there will be a human intervention in the system. The best examples is the ATM machine for soft real-time system. So even if the ATM takes a few seconds more than the ideal operation time, nothing fatal happens. Means there will be no disaster as such. Okay, so there may be some delay in printing the receipt. There may be some delay in ejecting the cash. So there may be some delay in processing the your card. Still, if at all it gets stuck, still you can call to bank and you can take it. So this is these are the alternative ways to handle it. So nothing disaster happens. So another example is an audio video playback system is another example of soft real time system. So what we uh, see in our cars, no potential damage arises if a sample comes late by a fraction of a second for playback. If at all there is any some delay of playing songs, still uh, no disaster will happen. So these are the examples of hard real time and soft real time systems.